So, welcome to the new lecture of this course, Fundamentals and Applications of Dielectric Ceramics. This is probably going to be the last lecture of this course. So, we'll focus on some more applications of these materials, and then we'll just summarize the course in this lecture. So, let's just recap the previous lecture briefly. In the previous lecture, we learnt about the piezoelectric measurements. What are different types of piezoelectric measurements, which are basically aimed at measuring the direct coefficient, which is basically you can say Coulomb per Newton, or they are measuring at indirect coefficient, that is meter per volt. And then we looked at how do you measure the pyroelectric coefficients. Pyroelectric coefficients is generally they are generally measured using measurement of pyroelectric current. Okay. And there are few methods in direct coefficients, such as direct cantilever method or direct cantilever method, direct load application method, and the interferometry, laser interferometry methods. So, these are most common methods to measure the piezoelectric coefficient using, and then we were looking at the applications. And we looked at one application of a piezoelectric material, which is in case of, which is basically about the running the gas lighter. One thing which I forgot to mention is that when you make piezoelectric measurements, you have to ensure that you are measuring the slope of basically the strain versus voltage, let us say, okay, or the charge versus the force. Basically, the measurement should be made in the linear region, right. So, linear region requires that the measurement is made at smaller voltages or smaller forces, otherwise if you go to nonlinear region, then the measurement may be wrong. So, basically you are looking at measurements to be made in the linear region. So, for example, if you measure for a ferroelectric we measure generally a butterfly loop. A butterfly loop is something like this. You can say something like this, okay. And this butterfly loop will have linear region somewhere here. So, if you measure at very high fields, for example, at very high fields you may get nonlinear region. So, you have to ensure that you make measurements at low fields. So, low fields measurements are required to make the measurement of indirect piezoelectric coefficient. Similarly, low force measurements will be required to make the measurements of direct piezoelectric coefficient. So, basically you are looking at the linear region measurements. Now, let us come back to again the applications of piezoelectric. So, piezoelectrics, as I said, are useful for we looked at gas lighter, simple application, but gas lighter is very trivial application, but they are most importantly useful for applications such as creation or detection of acoustic waves, acoustic or ultrasound waves. So, for example, let us say this is a piezoelectric. If you apply a pulsating field to it, which means at some point it will become longer, at other point it will become shorter. So, this size will change depending upon the signal sign of the signal. So, when this changes its sign, it creates what we called as these kind of waves, and these waves have frequency in the ultrasound range. So, what you can do is that you can use it for various methods. For example, nowadays we use it for breaking things like kidney stones. These waves can be directed on the kidney stones to break them. So, basically waves are directed onto objects such as kidney stones to break them, and once they break them in smaller pieces they can come out through urine. So, this is something that is possible. Another thing which ultrasound waves are useful for is for example, tissue imaging. So, for example, if you want to image the kidney, if you want to image the internal body parts. So, let us say you have some body parts here and you throw these ultrasonic waves, right. So, in the body let us say, this is the tissue, okay. It could be for example a baby, it could be something else. So, wherever you have fluid, you do not have tissues, the waves will pass through, but wherever you have tissues, the waves, part of the waves will be reverted back, all right. And the waves which are reverted back again analyzed using an analyzer here. So, you have a source and an analyzer here. So, by looking at the reversal of some of these waves, you can construct an image. You can see that which of the waves, from which regions the waves have not come back, and from which other regions the waves have come back, and accordingly you can construct an image. Let us say this is the image you will construct. So, from this region waves did come back. So, this is the region waves came back partially or completely, and from this region waves did not come back, right. So, this is how you can form the images by using image processing, and this can lead to imaging of tissues, babies and various internal organs in the body. So, this is a very important applications of piezoelectric materials, both invasive as well as non-invasive methods. Similarly, piezoelectrics are also used for transduction. Transduction is basically, you can say, detection of one type of energy by converting into other. So, for example, let us say you have this sea, and within sea you have these kind of torpedoes or objects. So, these are all, let us say, enemy torpedoes. If you have piezoelectric somewhere here, this is a small piezo. These have certain, since they make mechanical vibrations, they lead to acoustic waves. These waves can be detected by, piezos can detect presence of, for example, enemy ships, by locating the vibrations in the sea. So, the sea creatures will have different frequencies of vibration as compared to these moving things like ships and torpedoes and any other object inside the sea. So, they can be used to detect, for example, this. So, lot of naval applications which are called as sonar devices. They use these piezoelectrics for detection of these waves. Similarly, they can also be used as actuators. Actuators could be, let us say you have a piezoelectric rod, it can be applied voltage in such a fashion so that you have this linear transduction, linear actuation. So, you can have linear actuation, you can have cylindrical actuation, let us say. So, you have a cylinder, let us say of a certain thickness, and let us say you wanted to change this diameter di. So, by applying the voltage, you can change the length as well as diameter of this. So, this would be cylindrical actuator. Right. So, wherever you want change in dimensions, either in lateral directions or in circular directions or whatever directions, you can use these piezoelectrics because they work at very small voltages. And the good thing about them is they can be used for actuation at micron, at nano scale, because you can control the movement of these at those scales by applying very small voltages. Because you can see that the most of the piezoelectrics have this piezoelectric coefficient, for example, let us say 100 picocoulomb per Newton or 100 picometer per volt. For 1 volt of voltage applied, you can have a displacement of 100 picometer, which is nothing but 0.1 nanometer. So basically you can make nano manipulators, micro manipulators kind of devices. So you can say these micro and nano scale manipulation that is easily achieved using a piezoelectric material. For example, atomic force microscope uses a piezoelectric for manipulation. So these are certain applications of piezoelectric materials. Now let us get back to what we look at for. Let's look at the applications of pyroelectric materials. Pyroelectric materials, as we saw earlier, they are based on basically small pi is equal to del ps by dps by dt, change in polarization as a function of time or temperature. Sorry, it is not time, it is temperature. Now pyroelectric materials can be used for a variety of applications. For example, they can be used for infrared imaging, slash detection. They can also be used for gas detection and so on and so forth. So let me see, let me show you an application of pyroelectric. So let us say first let us see we look at the gas detection, or so let us say we have IR source, this is let us say IR source, and this IR source is basically, you can have a device to alter the signal, right. You can measure the change the intensity, or you can create a continuous signal, you can have a pulse signal and so on and so forth. So basically IR source followed by something to change its, and then let us say we have a chamber in which we have, so let us say this is gas chamber. Okay. So here we have gas in and we have gas out. Okay. And then we have, let us say here, so we have the pyroelectric detector. Okay. And basically what happens here is you have a particular gas, let us say specific gases which absorb a specific kind of radiation. So here we are talking about the IR, so we are looking at the, so what we have here is we have, what you do is that you first create a IR source directly to a piezoelectric. So this becomes your reference, right. There is nothing in between. The IR goes directly using whatever chopper and etc. you have directly to the detector. So similar kind of IR goes to detector, pyroelectric detector, which is used as a reference, and then you look at you basically pass this IR through the specific gas, and this specific gas will lead to some sort of absorption or whatever, and then IR is detected. IR is nothing but it will cause heating. So it will cause heating to the pyroelectric, as a result it will change in the polarization, and when it brings the change in the polarization, basically you will change the voltage. So we are looking at the change in the voltage by the radiation which is passing through the gas. Okay. And this, depending upon the presence of gas, how much gas is present, how much the radiation is absorbed, you will have different changes in the voltage, and that is how you can calibrate the system with respect to a reference, and you can measure the concentration of gas. So when you fire the radiation, so when the first time when the radiation goes from here, it does not go through anything, but when the radiation goes from here, it gets absorbed. So obviously you have to have a gas which basically absorbs IR radiation. If you have a gas which does not absorb IR radiation, then it is not very useful. So condition is gas should absorb IR. Okay. So, certain kinds of gases can be absorbed. So, correspondingly you will have a voltage with respect to a reference, and then you will have a V naught prime which is different from the reference depending on the absorption, and correspondingly you can measure the you can calculate the. So, this is basically used for pollutant kind of gases which absorb IR, like IR absorbing gases are things like carbon dioxide and so on and so forth, which as pollutants. Not every gas absorbs IR, so you cannot use it for every kind of gas, but it is useful for atmospheric pollutants. Okay. And then let us look at another application which is basically the infrared. So, another application which is used for which these materials are useful for are infrared detection, and they are basically the detectors which are present in things like so these detectors are found in lawns, homes, toilets, variety of places. So, basically what you have here is you have a pyroelectric, okay, which is so you have two metal pieces, okay. These are, let us say, conductors. This is a pyroelectric, and this conductor is coated. So, this is coated in a so this is basically a coating which is absorbent coating. Okay. So, and which when you connect them together, then they. So, now what you do is that you put them all together. So, when you put them all together, you bring them together. So, when you bring them together, it becomes like this. This is your, sorry, let me use the same color. So, this is pyroelectric, all right. On one side we have this metal, let me just shade it here. On this side we have another metal which is coated using a absorbent coating, all right. And now what you do is that you fire a IR pulse. When you fire an IR pulse, what will it do? It will increase the temperature of the pyroelectric, and what will happen is that when you fire the IR beam on the pyroelectric, the transmitting conductor on this side which is not coated allows the radiation to get in, but the other conductor which is coated by absorbing medium does not allow to leave it. As a result, you will have heating because you will have build up. So, on this side you have transmittance, but on this side you do not have transmittance. So, as a result you will have build up of heat, and this will increase the temperature of the pyroelectric. So, when you have temperature of the pyroelectric, you will develop some sort of charges. You will have, let us say, depending upon the pyroelectric coefficient value of this thing, and you will have a voltage that is generated across the circuit, right. So, this can be basically so if you want to do it more and more, you can just keep firing IR pulse from this side. It could be continuous, it could be pulse depending upon the application, and that is how you can use IR as a detector. So, for example, if you have a lawn, let us say you have a house here, okay, you have put IR detector here, this is the front door, somebody passes by. When somebody passes by, the temperature of this person will create a, so basically when human body is hot, it creates a IR, and this IR is detected by this detector, and because of change in the pyroelectric the polarization, it will turn the lights on or off. So, basically it can be used as a light saving devices. Similarly, in case of toilets, it can be in the toilet it can be used to operate the flush, because when a person stands in front of the toilet, the IR is absorbed by the detector, and when the person leaves, then the temperature drops, the IR stops. As a result, the feedback circuit will detect the presence of IR and the absence of IR, and when the person leaves, no IR is present, temperature will drop, and then it will release the water. So, this can again be used for making water saving. So, basically it can be used to make save light, water, etc. So, basically motion detectors and so on and so forth. So, a lot of applications. Similarly, based on the change in the similar application be used for IR imaging. So, when you go for example in the night, okay, so there are different objects at different temperatures. For example, in human body itself we have different objects at different temperatures, and you can image this using IR camera. So, I will show you one image which can be used to measure this kind of thing. So, let us say this is a image which I have obtained from Wikipedia. So, what you have here is, it is a thermogram, basically it is an image which shows changes in the local changes in the temperatures. What you have a human hand on which there is a snake that is wound. Snakes, as we know, are cold blooded animals and humans are warm blooded animals. So, you can see the temperature of the human hand is at about 32 degrees Celsius, and the snake, which is dark blue, is at about 22 degrees Celsius. So, you can see this very clearly. So, you can see from different color contours. So, this goes from 22 to 32 degrees Celsius. You can see that all the colors, there is a huge color variation which shows you that at a resolution of about 1 to 2 degree you can monitor the changes in the, and this is what basically is also used for night vision cameras. When you go do imaging in the night, these kind of materials can be used to create night vision imaging, which is basically nothing but based on temperature changes in the ambient, basically thermal imaging as we call it. So, these are certain uses of pyroelectric materials. Now, let us look at what we call as ferroelectric materials. So, every ferroelectric material can of course be used as a piezoelectric and pyroelectric, and similarly every pyroelectric can be used as a ferroelectric. But in addition, ferroelectric material has a very important use, which is to be used as data storage. So, just like magnetic material, it has this state of plus PR and minus PR. This plus PR can be 0 and this could be 1. So, basically this can be used for binary data storage, analogous to in a manner analogous to magnetic memory. And this will basically lead to non-volatile data storage, means the memory will not be lost, non-volatile. So, basically the data will not be lost when the power is lost, because this is at 0 field. So, at 0 field you have two states. In a normal RAM, this is the curve you have. So, RAM always needs power, right, but RAM is fast and magnetic memory is slow. So, if you can make a ferroelectric random access memory which will do the function of RAM because it is fast, but it will also be non-volatile, which means it will not lose the data. And ferroelectrics are also used for simple applications like camera flashes, etc., and they are of course used as piezos and piezo and pyro electrics. So, this is what we have done in this course. Let me now summarize the course. In this course, what we have done is we have looked at various aspects related to dielectric materials. So, just in a summary, let us say, so dielectric materials as we know are basically electrical insulators, and most of them happen to be oxides. That is why we initiated with our discussion on structure of dielectric materials. We looked at what is the role of bonding and crystallography in forming the structure of dielectric materials, and we saw that most dielectrics are ionically bonded and they make generally HCP based, FCC based or cubic packing of anions. So, structures are based on HCP, FCC or cubic packing of anions, where cations go and occupy the interstices between them, and for these what they follow generally what we call as Pauling's rules, which are based on electrostatistics considerations, where the idea is to ensure that cations and anions stay away from each other, but they are close to each other, right. So, anions cations are close to each other, but anions like ions are away from each other and unlike ions are close to each other, so that you have minimum electrostatic energy of the system. So, we looked at various structures of these dielectric materials. After that, we looked at what we called as defect chemistry. Defect chemistry is extremely important because presence of point defects, so basically from the perspective of point defects, right, and point defects will mean the presence of vacancies of oxygen, presence of vacancies of metal interstitial, oxygen interstitial. They give rise to extra electrons or holes in the system, and they are also dependent upon temperature and partial pressure of oxygen as well as impurity concentration. Presence of these point defects is very important from the consideration of dielectric behavior. If you have lot of defects in the material may turn very conducting. As a result, it may not be useful as a dielectric. But on the other hand, if you have methods to control these point defects, for example, by using appropriate temperature, by using appropriate conditions for synthesis in terms of partial pressure of oxygen, or by using dopants which can reduce the amount of these defects, one can use this defect chemistry knowledge to tailor the materials. And then we looked at what we call as dielectrics, dielectric fundamentals. We introduced quantities such as dielectric constant and dielectric displacement, polarization, dipole moment and so on and so forth. We looked at what are the mechanisms of polarization, and we saw that polarization happens at various frequencies, which is determined by the smaller to biggest entity. So, electronic polarization, ionic polarization, dipolar polarization, interfacial polarization, and we move from electronic to ionic to dipolar to interfacial as the frequency decreases, because the size of the entities also becomes larger. And basically the electronic and ionic polarization are depicted by resonance at certain frequencies below which you have these below which these become active, whereas the dipolar and interfacial polarization show relaxation mechanisms, and correspondingly you see certain behavior of dielectrics. And then we looked at the AC behavior, basically what happens in AC field, time dependent analysis, and then we also looked at the impedance analysis, right. So, this was basically from the perspective of what we call as linear dielectrics, the dielectrics in which the polarization versus electric field behavior is linear. So, when you plot P versus E, it is linear. Then we move to learn about new dielectrics or different dielectrics which are called as nonlinear dielectrics, and in that category we mainly learnt about piezoelectrics, pyroelectrics and ferroelectrics. So, while normal dielectrics like linear dielectrics are used for typical capacitor applications, the piezo, pyro and ferro, they are useful for variety of different applications. You can use them as sensors, you can use them as actuators, transducers, you can use them for imaging devices, you can use them for memories. So, they have fantastic behavior because they exhibit properties which are not exhibited by normal dielectric materials. And we also looked at details of the crystal structure and the physics of these materials, the elementary physics of these materials to understand their behavior. So, this is basically the overall summary of this course, in which we have looked at structure, the defects and the properties of these materials from a fundamental perspective, and we also looked at some applications of these materials. And I have also suggested a few books about these courses in the beginning, which you can read to improve upon your knowledge. You will have weekly assignments. I am sure they will be going on as the lecture go, which will also test the knowledge of you, this course periodically. So that and I recommend that you do not get dependent only on the lectures, but also read the books. Okay. So, we will stop here. I hope you have learned from this course the fundamentals of these materials. Of course, if you have any questions, you can get back to us on the portal through my TAs or directly to me, and we will be happy to answer your queries. So, hope you enjoyed the course. Thank you very much.